Welcome back, everyone. Today's video is going to be like a two-part deal. Basically, we are going to explore the solar system if it were made of entirely Earths. So, what I mean by that is we are going to um, basically replace every planet in the solar system with the Earth. So we're going to have multiple Earths. And the reason we're going to do this is because I want to show y'all what what it would be like having the same density as Earth's atmosphere at these relative distances from the Sun. So obviously, an Earth at Mercury's orbit is going to be uh, way too hot. Same with Venus. Our Earth is normal. Mars might be okay. But then you've got the outer worlds, Jupiter, Saturn, Uranus, Neptune, which are obviously going to be far too cold. But before we get into that, actually the inspiration for this video comes from a book called A World Out of Time. It's by Larry Niven, and I believe it was written in 1977. It's the story about a man who's cryogenically frozen in the 90s, then finds himself aboard a spaceship, a ramjet, I think it's called, scramjet. I can't remember the term for it. The interstellar spacecraft that scoops up hydrogen, interstellar hydrogen, and uses that as fuel on its way to the stars. But yeah, he steals like one of those, and I think he circles the galactic Milky Way, the core of our galaxy, and the time dilation effect allows him to arrive a million years into the future. He's trying to avoid basically a controlling police state. The government's become overbearing and too controlling. So he comes back. I think it's like a million, might be a couple million years later. But regardless, this would not happen in the real world. And in his story, the sun has basically started to go into its red giant phase, and the Earth has been moved from its current orbit all the way to Jupiter. It's now a moon of Jupiter. I know in the last video, if you watched it, we had basically a Jupiter in Earth's orbit, right? We replaced Earth with Jupiter, and the reason we did that is so we could discuss exomoons. Um, there are, I think, over 100 candidates where we've identified stars in the universe that have a gas giant within the habitable zone. So it's while the gas giant couldn't play host to intelligent life, its moons certainly could if the conditions were just right. So the last video we proved that an Earth circling a Jupiter, sized world around that size in the habitable zone is completely viable. Of course, you'd have 5-6 days of light and darkness because any any Earth around a Jupiter at that distance, well, at any distance really, is going to be tidally locked. So remember, it's got to be close enough to the planet to be within its protective magnetic field, but not too close where it is. Excuse me, where it's. Oh my God, my brain is just not working. I should have made a cup of coffee first. I apologize, y'all. It's got to be close enough to be inside the gas giant's magnetic field, but not so close to be inside its radiation belts. Okay, that's what I was trying to say. So today, what we're going to do is we are going to, like I said, replace all the planets with Earth, so you can see how different distances from, I'm sorry, man, my brain is just fried this morning. I'm still waking up apparently. But yeah, you can see that the different distances, of course, affect the Earth differently. And we're going to discuss how much sunlight, and I can do that right now actually, how much sunlight each world gets. Okay, so obviously, Earth, we get normal sunlight here. That's the standard, right? As you go farther out, Mars only gets 40% of the solar energy that the Earth does. So it's definitely going to need some help to be a warm planet. Even if we were to drop a entire Earth atmosphere, boom, right there on Mars, and give it a bar of thickness at sea level, it's still going to be a very cold world because it's only getting 40% the sunlight that the Earth is. Now, when you move further out, right? Ceres, for those of you that know, is a asteroid, well, dwarf planet, whatever you want to call it. It's really both. It's the largest asteroid and the nearest dwarf planet, and it orbits within the asteroid belt between Mars and Jupiter. So somewhere in this region, right? It gets about 15% the sunlight that the Earth does. Now, 15% doesn't sound like a lot, but it's still plenty to grow most Earth vegetation, including foods, fruits, vegetables, things like that. And the reason it's enough is because 15% is not really 15% of what we receive on Earth. Okay, when we think of how much sunlight the Earth gets, we don't take into account that the atmosphere reflects and absorbs about half of that. So, whatever units you're using, right? We here on the surface, and that includes our trees, our orange groves, and everything, our agriculture, it receives half of the sunlight that it could because the atmosphere is both reflecting away and absorbing a lot of that energy. Okay, so 15% is not that bad because really on Earth, to be honest, we're getting 50% of the sunlight that we should. But on Ceres, we'd be getting the full. Sorry, I said 50%, right? On Ceres, we'd be getting 15%. So 15% is not that less than 50. So again, most vegetation should grow there. Now, things start to get drastically different, though, when you get to Jupiter. Jupiter only receives 5% of the sunlight that the Earth does. So at Jupiter, you're really starting to need some help to grow anything. But, that help could be in the form of mirrors, which are relatively cheap to make. I'm specifically thinking of Callisto. Callisto is extremely rich in water and volatiles, things like nitrogen, phosphorus, all the building blocks of life, what we call organic matter. So, yeah, at 5%, it's still possible to grow things, and it would still certainly be very bright. You still couldn't look at the sun directly. But yeah, at 5%, you're going to need some help. You're going to need some mirrors. You got to get it up to at least 15%. So you're gonna need some mirrors and whatnot in place. But solar energy as an energy source is still very viable, even out to Jupiter. Now, of course, this is where my interest in the solar system pretty much ends, is with Jupiter and its moons, because I know people are a fan of Titan, but Titan at Saturn is receiving 1% the sunlight and solar energy that the Earth does, and that is at its cloud tops. Remember, the atmosphere of Titan is going to absorb and reflect like 90% of the sunlight. So it's getting 1%, and 90% of that is either being absorbed or reflected. So very, very little light reaches the surface. It's extremely dark on the surface of Titan. Moving further out, of course, you've got Uranus and Neptune. At Uranus, you're getting 0.25%. So not 25%, but a quarter of 1%. In other words, the Earth receives 400 times the sunlight that Uranus does. Okay, obviously we're beyond the realm of being able to grow any kind of agriculture. And then at Neptune, finally, you have 0.1% or 1,000th the sunlight that the Earth receives. So, but yeah, let's get to it. I've got the model all set up here. Let's see, solar system of Earths. There we go. Yep. All right, so there we go. So as you can see, every planet in the solar system, this is the inspiration for the thumbnail, every planet has been replaced with Earth. And I was very, excuse me, sorry about that. I was very exact too. I looked up the exact distance of from the sun of all these worlds, okay, and replace the worlds with Earth. So, and I did already go forward several years because, to be honest, it's going to take many, many years for Earth's average temperature to drop and increase relative to the distance from the sun. So, let's start at Neptune, right? A Neptune Earth, very dark, right? Oceans look almost completely frozen. Now, they will eventually completely freeze over, but you've still got this band of a little bit of liquid, right? But at Neptune, there's, like I said, 1,000th of the sunlight that the Earth gets. So this will eventually freeze completely over. The where are we? The average temperature is minus 150 Celsius, right? And Fahrenheit minus 240. So if we look at what that looks like, right? Virtually no difference. Like literally, I know it looks like the white would be hot and the blue would be cold, but you got to look at the graph down here at the bottom where the mouse pointer is. There's 1 degree of difference from the poles to the equator. 1 degree Celsius, I should say. So yeah, the entire world is unbearably cold. For my fellow Americans, that's minus 240 to 241 in Fahrenheit. So extremely cold. So the coldest Antarctica's ever been, I think, is minus 100, right around there. So unimaginably cold. All right, now let's go to the other extreme, where we've replaced Mercury with an Earth. Let's see how that's doing. All right, we still got some clouds. Let's see. There we go. Start the simulation. Looks like all the water is gone. Let me check. Let's see. Water. Yep. Not a milligram. So all the ocean floors would be exposed. There'd honestly probably be, for a long time, a very thick, like a Venus level haze of steam, as all that all that water vapor is going to go up into the atmosphere, and it's going to superheat the planet, because water vapor is the largest, most contributing greenhouse gas here on Earth. I know we talk about carbon because it's more potent, per molecule. It's better at trapping heat, but there's far more water vapor in the atmosphere than there is carbon dioxide. So water vapor is actually the major contributor to our Earth's temperature. But we can't really do much about there being water vapor in the air. We can affect carbon levels, though, so that's why so much attention is paid to carbon and not really water vapor. But honestly, I feel like they should really take both into account, and maybe they do. I'm not a meteorologist or a climatologist, so. All right, let's see what Venus looks like. How's Venus doing? Let's see. Now Venus is unrecognizable. Let's see what happened here. All the water's gone. Oh, okay. So, I guess because the Earth at Mercury's orbit is so much closer, the solar wind has stripped it of both water and hydrogen. But here at Venus, we've got, and the surface is totally unrecognizable. I don't know what happened to the surface, but yeah, we've got a very, very thick hydrogen atmosphere. Now, eventually, charged particles from the sun are going to strip that hydrogen away from the Earth. We'll lose quite a lot of hydrogen at our current distance, so even closer to the sun, the solar wind's going to be even more powerful, and it's going to strip that too. So, obviously, Earth is going to be normal. There's just a few more I want to check out here. Well, let's check out Mars. How is Earth doing at Mars? Ooh. Oh, wow. That's unexpected. So, you've got a band of, you got some city lights too. The people are still surviving here. They're having a rough time though. Yeah, you've got this band along the equator, and I guess really the Gulf Stream. That's not the equator. This is above it, but that's probably because of the Gulf Stream. Again, this is the path that hurricanes take when they hit the United States. That's actually the ice freezing has caused a lot of land to be exposed. So, but yeah, that's really surprising. Let's see what the temperature is. Oof, minus 50 Celsius or minus 58 Fahrenheit. Yeah, basically Antarctica. So, let's see. At the equator, yeah, the warmest it gets is 42.4 Celsius. Should be about the same, yeah, for Fahrenheit. Now this is actually not going to be true. This is probably due to the way they created Earth's model. You know, making things fit the way that things are on Earth, not necessarily, creating a model from scratch and whatnot. The end result was more important than the process of getting there. So, if we were to take the Earth and replace Mars, it would not be this cold. It would be cold, but it would not be this cold. This is wrong. And I know that sounds like cope, because I'm a huge Mars fan, but the reason why this is wrong is because, or I know that this is wrong, is because the surface of Mars does get up to 70 degrees. So our hottest temperature is 120 or so. Think like Death Valley or right along the equator during summer, the peak of summer. Places on the Earth reach 120, maybe even a little bit more, a few more degrees, maybe 130. I don't know what the hottest recorded temperature is, but that's extremely hot. That's life-threatening, obviously. So, but yeah, so this is wrong because you from 130, let's say, to 70 is a 60-degree temperature change. So it should be 60 degrees colder than the Earth, not not 100, So something's gone a little crazy, so excuse me. But yeah, so that's Earth at Mars's orbit. Now, at Jupiter, you can imagine it's going to be even worse, right? Yeah, so we're starting to get into unbearably cold temperatures here. Now, let's do one more thing. I'm not even gonna give Uranus the time of day. Nobody likes that planet. Nobody likes Uranus. Haha. Um, I want to do one thing. So the sun, its luminosity is our gold standard, right? Just like the Earth's distance is one astronomical unit, the sun is one luminosity. So we judge all the other stars based on our star. A luminosity unit is the amount of solar energy that our sun puts out right now at this point in its life. Obviously, it's going to get, like every billion years, it's going to get 10% hotter for a while, 10% more luminous. So let's do a little experiment. Let's say it's 2. Okay. I really need that to be 1. Okay. All right, good. We kept everything. All right, you see the temperature's climbing. Okay. Because we've doubled the output of the sun. And noticeably, right? This is where Earth usually is now. Earth is really inside the temperate zone. It's really where Venus is now in relationship to the habitable zone. So, and Mars is right smack dab in the middle, okay, of the new habitable zone. So we'll probably see that temperature rise. I'm going to speed things up, let several years pass, so we can watch the temperatures change over time. Yeah, see, that's definitely rising. I don't know how hot it's going to get, but we will soon see. So the reason why I double the sun's luminosity, though, is because when it comes to terraforming other worlds, we are going to be, especially with Mars, most likely reflecting more sunlight down to the surface. So with space-based mirrors and carefully balancing out the gravity of these worlds. Hang on. This is making me dizzy. Let me get the sun in the middle. There we go. Carefully balancing out the gravity of these worlds. We can, like I said, put a huge planet-sized mirror. Obviously, machines would have to build it for us, but put a gigantic mirror in orbit around Mars. Voice sounds terrible today. I really apologize for the audio, y'all. But yeah, we could use the sun's light pressure and the gravity of Mars to pretty much keep it in place. All right, shoot, I lost track of our new Mars. Okay. Still looks relatively chilly, though. Yeah. So the average temperature is not getting above freezing, so interesting. You can see the ice right here, growing and shrinking with the seasons. I can't tell if it looks like it might be getting bigger overall, but still, it's not getting above freezing. So 0, it's freezing in Celsius. See, in Fahrenheit, it's 32. So, but yeah, so the reason why I did that is because when it comes to Mars, like I said, we can increase the amount of sunlight that Mars gets, but still, very, very cold. There, of course, it won't be this frozen even at 18 degrees Fahrenheit, because parts of the world, the equator, for instance, gets above freezing. It's about 41 degrees Fahrenheit. So the equator would be chilly but habitable. anyways, yeah, so that's going to be the video. I want to thank you all for watching all the way to the end, and I really apologize for my voice. It sounds scratchy and gravelly. I don't know what's going on. I think it's the dust or the I don't know. So, um, anyways, thanks for watching. Please be sure to leave a like, and if you've got a suggestion, leave it for me. I'm very open to uh, doing some of your ideas. At one point, I want to do Tatooine, discuss that, and how some planets orbit not one star, but two, and what that means for our search for life. So, anyways, like I said, leave me a like if you can. Consider subscribing, and thank you so much for watching. Take care, okay? Bye bye.